Okay, so we defined. So we are studying the planar graphs, right? So you saw this proposition that K5 and K33 they are not planar graphs, right? So this is fine, right?
Yeah.
Okay. So the next definition is so a curve in an image. So we are defining what is a curve. In the image of a continuous map from 0, 1 to R2. So yeah, so a curve is nothing but the image of a continuous map from 0, 1 to R2. And a polygonal curve is a curve composed of finitely many line segments. Okay, so it is called a polygonal UV curve. If it starts at U and ends at V. So what is happening is, so suppose we have this R2, right? So suppose this is U and suppose this is V. Suppose like this you have. So this is a polygonal curve because it is just it has many line segments. So this part is one line segment, this part is one line segment, like that. It is a union of 4 line segments. So this is an example of a polygonal UV curve. Okay.
Yeah, it's okay.
Right. So the next definition is so a drawing of a graph G is a function defined on the vertex union the edge of the graph that assigns each vertex V a point f of V in the plane and assigns each edge with endpoints U and V a polygonal FU, FV curve. So the image of the vertices are distinct. and a point in, suppose E is an edge and E prime is also an edge. So FE intersection F of E prime. So that is not a common endpoint. Is a crossing, right? So what is happening is, so for each vertex, the image will be a single point, so that is fine. And for each edge, we are assigning a polygonal curve from FU to FV. Suppose the endpoint is U and V. Now, suppose two edges are intersecting. So it can happen that either they are intersecting at the endpoints, or it can intersect in between. So that is a crossing, right? So that is what the last point says. That if in the one image of the edge and with intersection with another image of the edge is not a common endpoint, then it has to be a crossing. So like this, they are meeting at a crossing. So that is called a crossing.
Upon in FE intersect with the FE prime. There is not a common endpoint.
Yes, that is not a common endpoint. Yes.
The crossing, what does it mean? There is not a common endpoint.
Yes. So the thing is, suppose two edges are there, right? Suppose these are two edges, then it can happen like that they are intersecting like this, which is not a vertex, or it can happen that this is an edge and this is another edge. So they can intersect in these two type of ways, right? So in the second case, so this is a common endpoint, right?
Mm.
So this is a vertex and this is a common endpoint for these two edges, but this is not a vertex. So this will be called a crossing.
Mm.
So if it is not a common endpoint, so this is f of e and this is f of e prime. Similarly, this is f of e and f of e prime,
Mm. Yeah, yeah, yeah.
right? Okay.
Mm.
So yes, so we
About,
can have, yes,
about let's explain about 0, 1, 2 as well.
yes, 0 1 2 r square is this one, right? So the
Mm.
thing is, we have a continuous map, right? So any continuous map which is from 0 1 to r square. So will the image means we can draw the graph, right, of that. No, this one is the usual graph, the graph for the continuous functions. So if we have a graph from 0 1 to r square of a continuous map, that is called a curve.
0, 1, 2 as well. 0, 1, 2 as well.
Yes.
That's your line.
No, that can be anything, right? It is a continuous curve, right? The curve
0.
can be anything. Means I can have like this, right? So from I can have like this, means I can have like this. Anything, any continuous curve I can have, right? The image, the domain is 0 1 and the image is R2.
Actually, 0, 1 is also the same with R, is right?
0 1, yes, yes, that is that we can do. Means there is
Mm.
a bijection that we can define, but yes, for now we are doing only from 0 1,
Oh, 0, 1. Mm. Yeah, yeah, yeah.
right? And the polygonal curve is a curve that is composed of finitely many line segments. So it is only so for example, if I have a curve like this, that is some sort of parabola or something like this, so then that is not a polygonal curve. The polygonal curve is only those type of curve that can be written as finite union of finitely many line segments. So like this, so it has to be line segments. So it can have, suppose this is a straight line, that will also work, but it can have more than one line segments also.
Yeah.
right? Okay. So next we formally define the planar graph. So when a graph is called planar, so for that the crossing definition was needed. So a graph is planar if it has a drawing. So we know what is a graph drawing now by definition, without crossings. So if you can draw a graph without crossing, then it is called a planar. So such a drawing is called a planar embedding of G. Planar embedding of G. And a plane graph is a particular planar embedding of a graph. Of a planar graph. So for example, suppose I have this is one graph. So suppose this is there, and I have another thing. Suppose this is my graph. So this graph has a crossing, but actually we can have a, but the graph is planar because we have a planar embedding. So what I can do is, so right. So this is 1, 2, 3. Suppose this is 1, 2, 3. Yes. So this graph is actually the first graph has a crossing, but the new graph we can have a planar embedding of G, such that we can show that it is actually planar. So it has a planar embedding.
Planar embedding.
Right. The second graph is a planar embedding of G.
In a plane graph.
Yes, a plane graph is a particular planar embedding of G. So there can be many planar embeddings. So plane graph is just a particular planar embedding of a planar graph.
Here in this example, what's the plane graph?
Yes. So for example, this one you can take as the plane graph, right? Because so this is a particular planar embedding of the G, right?
Yeah.
Okay. Okay. So next part is a curve is closed if its first and the last point are the same. So, for example, here you are starting. So you draw a curve and you come back. So if the first point and the last point are same, then we will say that the curve is closed. So this is natural definition, and it is simple. If it has So if it has no repeated points except the first and the last point.
Mm.
So for example, this is simple
Mm.
because there is no common point. But suppose I have another closed curve, so that is going like this and then coming back like this. So then this is not simple because this point is getting repeated on the curve. So this one is not simple,
Mm.
right?
Mm.
Okay. So yes, this is a simple curve. I think that is fine. Now the next definition is, so an open set in a plane. So define what is an open set in a plane. So an open set in the plane is a set U which is a subset of R square such that for every P belongs to U, all points
Mm.
within some small distance from P belong to U. So if it is holds for every such point, then we'll say it is an open set. So what is it saying is within some small distance. So suppose you have a set like this, right?
Mm.
So suppose this is a subset of R square. Suppose I take any point and then I am able to find this region that is out that is surrounding this
Mm.
point. That the distance, suppose this is my point P, such that every point also belongs to U within that small distance. Then and it is true for every such point inside U. So then we will say that U is open.
On boy,
Yes,
not
yes.
some boy.
No, no, it is for every. So here it's saying for every point P belongs to Q.
Oh,
All points
okay.
within
So
some.
in the border,
Yes, yes.
in the
Border
little
it will.
boy,
Yes, yes. Border it
in.
will not work. That's why yes. This is not an example. I'm just explaining. Yes.
Mm.
So for example, yes, this is the border points will not work. Yes.
Mm.
So the thing is, what we can have is, so instead of that, so we can have some dotted region, right? So dotted region means the border is not there. So in that case, it will work, right?
Mm.
Because we can choose always a small distance, such that every point inside that
But
is
but it's the also this definition. It also work with closest. Is right. In closest, we uh, for some boy we also uh, have on point in the some small distance.
yes, yes. But it has to be. It is true for every. It should work, right? But in closed set, that is not the case, right?
In closest, every boy also work. Is right. Except the powder. I think the powder is the K boy of open set or closed set. Is right.
Yes, yes. The border thing will not work, right? In a closed set, it is fine, but for open set, the border points will not work. So closed set is different, right, from open set. That's why.
Mm. The I read the definition, but I I, I confuse what's the difference between cloud and open set in this definition.
Yes, yes. So the open set, what we are defining is for
Yeah.
every point in the open
Uh,
set. there should be some small distance such that from that point, if I consider all the points within that small distance, everything should belong to U, right? So that is the definition of open set, right?
Mm.
But closed set, it is different, right? Closed set is because the closed set contains the border points also, right?
Mm.
But that will not work, right? So for border points, we don't have this condition. So closed set and open sets are different, right?
But but uh, but every point. So this definition accept the exclude the border is right.
Yes, yes. So
So
border point.
if we exclude the border, the definition of open set and closed set is the same. Is right.
Yes, yes.
So when we read this definition, we cannot distinguish between open set and closed set. Is it
Yes,
right?
yes, because closed set is different. Yes, because it has other conditions.
Yeah. If it include in the limit boy, that's a closed set.
Yes, yes.
Uh, open set. Yeah. Mm, mm, I am trying to remember the definition of open set and closed set in topology.
Yes, yes. So
Yeah,
yes, that is the same definition. Yes.
yeah.
So closed set we have to include the limit points. So but limit point will not satisfy this thing that for every small distance we will find some small distance such that every point within that thing will work will belong to that set. That may not be true for the limit points. So that's why there are two different things: open set and closed sets.
Mm, 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 mm. Open set. Yeah, open set. Yeah, open set. Yeah. This is it.
Right.
Mm.
So next one is, so next they are defining what is a range in an open set. So sorry, a region. A region is an open set U that uh, contains a polygonal UV curve for every U comma V belongs to capital U. So that is the definition of a region. So a region is an open set. So open set, the definition of open set should work. But other than that, we are having one more thing, that there should be a polygonal curve between U and V for every 2 points U and V. Right? So the thing is, it can happen that suppose I have an open set like this, and I have another open set like this, right? But the thing is, this is not need not be a region, right? Because from here, if I choose one point, and here if I choose one point, so there is no polygonal curve between U and V, because they are in two disjoint things, right? So yes, so we'll call it a region. So this part can act as a region individual, because between any 2 points, I can draw a polygonal curve between those two endpoints, right? So that is a region,
Mm.
right? And the faces of a plane graph are the maximal regions of the plane that contain no point used in the embedding. So that is a face of a plane graph.
Mm.
So for example, if you we have a okay, I think that is fine. So the thing is, if we consider a plane graph, so suppose just if we consider, so K5 we saw that is not a planar graph, but K4 if we draw, so we can have a planar embedding or a plane graph of K4, right? So so two more edges is there. So this is one edge, and another edge I can draw like this, right? So this is a planar embedding. So now face we can do like this. So this is one face. So this is the second face. So this is a third face, and the outside is another face. So this is the regions, maximal region that this graph divide the whole plane into. So
Mm.
so that is the, so this outside is also one face. So here are four faces of them.
Mm.
Okay,
Yeah, yeah. Mm.
right. So that is the next point they are making. So a finite plane graph G has an unbounded face, has one unbounded face. That is the outside one, also called the outer face. Right, and the, so that is one observation. And the faces are always pairwise disjoint. So that is by definition. So they are pairwise disjoint. Suppose points P and Q, they belongs to suppose the plane in R2 lying in no edge of G. It is, suppose it is not on any edge of G, are in the same phase. If and only if there is a polygonal PQ curve. Curve that crosses no edge. Right. So the same idea. So suppose let us draw again the K4. So these are the vertices, and this is the last edge. So the thing is, suppose if I take uh, points here, this is P and Q. So I can always draw a polygonal curve between P and Q. So then we'll say that these two points lie on the same face. But on the other hand, if I choose P from here and Q from here, so any polygonal curve that I draw, it has to cross the edge at one point. So that is, then we can say that P and Q does not lie on the same face. So that is what they're saying. So on the same face, if and only if there is a polygonal PQ curve that crosses no edge.
Unbound is fine. It was
Yes,
outer fine. Where
yes,
is
yes. You can put the outer here also. I can choose any 2 points. The outer area also you can choose.
outer out of the graph is fine.
Yes, yes. That is also.
One outer fine. Okay. Yeah, yeah. Okay.
Right. So up to this is fine, right?
Mm.
Okay. So next observation is, So a finite plane graph G has one unbounded face. This I also saw. Sorry. So the next one is, so in a plane graph, every cycle is embedded as a simple closed curve. With
Curve,
yes,
cloud curve.
right, and some faces lies inside it, and some are outside. So, for example, if you see this one, so this is a cycle in the graph, and this is a simple closed curve, and these two faces are inside it, and these two faces are outside it. So that is the observation,
Mm.
right? Okay. So next we have one theorem. So it is called the restricted Jordan Curve Theorem.
Mm.
Okay. So the statement is a simple closed polygonal curve C consisting of finitely many segments partitions the plane into exactly two faces. Each having C as boundary. Okay.
Mm. Single curve. Mm. This one partition. Two five. It
Yes.
haven't seen it already. Uh, close. Okay. I set at the cycle divide to partition is right.
Yes. Yes.
Hmm.
So they're saying that you have a closed polygonal curve. So it means that,
Hmm.
so suppose the starting vertex, you have some polygonal curve like this, right? And you come back and close it here, right? So there is a closed polygonal curve. So it divides the whole plane into
Hmm.
exactly two faces. So this is the inner face, and this is the outer face, right? So that is the theorem saying. Okay.
Yeah, yeah,
I think this is fine, right?
yeah.
Okay. So I think that is fine. The next definition is do we define what is a dual graph? The dual graph G star of a plane graph G is again a plane graph. So is a plane graph whose vertices correspond to the faces of G. Okay. And the edges of G star correspond to the edges of G as follows. So if E is an edge of G with face X on one side and face Y on the other side, then the endpoints of the dual edge E star belongs to the edge of the G star, that is the dual graph, are the vertices X and Y of G star that represent X and Y of G. So this is the definition dual graph. So let us see what they are saying. So they are saying that so suppose I have a plane graph, then I know that there are faces. The G star, the dual graph, will take the faces as the vertices. Okay, and those two faces will be adjacent the dual graph if they have a common edge between them. So let me show an example. So we'll take our K4. So this is our K4. Right. So now the G star will be this will be the vertex. So this is one vertex because this is one face, This is one vertex. This is one vertex, and the outer face will be one vertex. So there are again four vertices. Now what are the edges? So now these two faces, they have a common edge between them. So there will be an edge like this. Similarly, this edge will be there because there is a common edge between them. So this and this, there will be an edge. Right. So for every, so this is the graph clear? So for example, this is an edge between this and this. So there
Mm.
will be an edge.
Mm.
This is an edge between the outer one and the inner this one. So there is an edge. And similarly, this is another edge that is between the outer face and this face. So that is an edge. And similarly, this edge and this. So the blue vertices are the vertices corresponding to the face, and the red will be the edges. So this thing total will be our G star. There is a dual graph.
Mm. Mm. I read again.
Yes.
Oh, yeah. The do graph we can understand it, but the dual graph that's mean the a clone of one graph into many into two versions, right? Yeah.
No, no, dual graph. No, I did not get it. Tell again. Dual graph is.
That's mean we have one graph and we clone it in other image. Image.
Yes, yes. So yes, we are defining a dual of
That's
that
it.
graph.
A copy. A copy.
Yes, not exactly copy, but
With
uh,
matching matching vertices to vertices and edge to edge is right.
yes. But the thing is, we are defining a new set of vertices here. The faces of the original graph are my new vertices.
The
So
pen.
it can happen that there are more than, so for example, in this example it coincides that the number of vertices are same because number of faces are also four, but it can happen that there are different amount of vertices in G and G star. So
Oh,
that is also possible.
oh, oh.
Right.
This
Right.
happened.
So
Oh.
for example, we can have one more. Let it be clear. One more example. So suppose I have this graph. So here total there are four vertices, right? So
Hmm.
how many faces are there? There is only two faces, right? So this is one face and one is outer. So there are only two faces, right? So here what will be the edges? So one edge is connecting because of this edge that is sharing. One is connecting due to this one, right? And one is connecting due to this one. And there is a loop because this edge is crossing. So this is my dual graph,
Oh, wait. If E and S of Z with the phi
right?
S on one side and Y
On
in
the other
other
side.
side, then the end bond of dual S what is it? SY.
So it is saying, suppose E is an edge of G with face X on one side and face Y on the other side, right? So let us see an example. Suppose this is my edge E, right?
Then the endpoint of dual graph S status the vertices SY of the present S and Y of the
Right.
present S and Y of the. What does it mean? Present S.
Yes, yes. So for example, this is the edge I am taking, right? This is the edge of the graph, original graph, right?
Mm.
And suppose this is my face X and this is my face Y, right?
S.
Face. This face is capital X. Suppose this face I am naming it as capital X, and this face I am naming it as capital Y. Right.
Oh.
So now this is an edge between. Let me write down. So suppose this is my capital X and this is my capital Y, and this edge is my E, right?
Mm.
And then it satisfies the condition, right? So E is an edge of G with face X on one side and face Y on the other side, right?
Mm.
So now the endpoints of the dual edge. So this is E star.
Mm.
So this edge is my E star. This edge is my E star.
Mm.
So that are the vertices X and Y of that represent capital X and capital Y. So this is my small x and this is my small y. So
Mm.
because these are the new vertices in my G star, because this x and this y are faces.
Mm.
Now see, now I think the definition is clear, right? Read it once, it will be clear.
Yeah, yeah, yeah. And other S, Y to this, and this outside, outside, this outside, one,
Right. So for example, here also,
three,
suppose I take this one as my edge, right?
uh, uh,
And these two faces are on the opposite side, right?
uh,
Of this edge. So there should be an edge connecting these two things.
yeah, yeah, yeah. It's okay. Mm,
Yes, but what about this loop? Why is this coming? So
mm,
suppose if I take this one as my edge, right? So it has two faces. So it has one face this side and one face this side. But actually these two are the same face, right? Because this is the outer face.
mm,
So that's why you have to connect with each other. So that's why you are getting a loop,
mm, mm. Yeah, yeah. Got it. Mm,
right?
mm. Yeah,
Right.
yeah.
So the observation is this is a plane graph, but it can have in the dual and it does not have any loop, but the dual can have a loop. So that is the observation. So, so a simple graph, or you can write a simple plane graph, may have loop, loops and multiple edges in its dual. So, for example, here also we have multiple edges also, right? So between this and this, I have one edge, two edge, and the three edge. So multiple edges also you can have in the dual one, right?
Mm,
So a cut edge of G becomes a loop in G star. G star is the dual. So I think this is clear because
mm,
the faces on both sides
mm, mm, mm.
because the face on both sides of it are same. So that's why it becomes a loop, right? For
Mm,
example,
mm.
here
Yeah, yeah, yeah.
there is a cut edge, so that's why that is occurring.
Right, right. Yeah.
Yes, and the multiple edges arise in the dual when
Mm.
distinct faces of G have more than one common boundary. Right, so this is also clear. So we will have multiple edges when suppose this is a face and this is a face. So they have more than one common boundary. So then we have multiple edges, right?
Mm. Yeah.
So I think the definition is clear, right?
Yeah. Yeah. Mm.
So today we'll stop here now. Okay.
Okay.